All right, let's talk about interval of convergence. So we have three options when we talk about convergence of power series. Now again, remember power series are saying, I'm going to try to find a polynomial that approximates a non-polynomial. Okay, that is the whole purpose of a power series. Now, it might only converge at the point of intersection. So we saw yesterday when we looked at 1 over 1 minus x. And then we saw, like, when you just put in that very first point, it was like, well, it only converges right there, right? So it is possible, like, if you have even an infinite series, that it only ends up converging at that one point. It also can be convergent everywhere. Sine and cosine actually have infinite polynomials that you can find that converge for all real numbers, okay? Or it might just be on an interval. Like we actually found with 1 over x that the series x to the n was only good, right, for x less than 1. Now notice A here, that's your center. So what that means here, but just to give you some context, that means my radius of convergence is what we call this r, must be 1, and my interval of convergence, if you look down here on our diagram, must be between -1 and 1. And that's how the inequality works. It also means that you can take the center and add and subtract your radius, and that's how you're going to find your interval of convergence. So it might just be at x equals a, it might be for all real numbers, or you might end up having some interval here. So let's look back at how we would show this. For what values of x will this power series converge? Well, we can use geometric series to say that absolute value of x must be less than or equal to 1. And so I know that at -1 to 1, I'm going to be convergent. Now, one thing that we would want to do is we'd want to test our endpoints. So if x is equal to -1, will this converge? We know with geometric series that it doesn't. So we'd want to test that no. Same thing when x equals 1. You'd have 1 plus 1 plus 1 plus 1, or -1, and then plus 1 is 0, but then -1, it's like those oscillate, but they don't converge to 0. So you're never going to get anywhere. Same thing with 1, you're just going to keep adding and adding and adding 1. But let me show you the long way of how we're actually going to do this. So we're going to use the ratio test in order to find this. And remember, for absolute convergence on our ratio test, a sub n minus 1, a sub n plus 1, excuse me, over a sub n must always be less than 0. Well, x to the n plus 1 is x to the n times x to the 1. These cancel, and that's also where this comes into play. Okay, so we're going to be using the ratio test on more complicated functions in order to figure out what this interval of convergence is. Let's do that for these series here. So again, I have something now a little bit more complicated, and I'm going to use the ratio test to find this. So take the limit as n goes to infinity of a sub n plus 1. Now, when I divide by a sub n, that's the same thing as multiplying by the reciprocal, and I need this to be less than 1 in order for this to be absolutely convergent. That means that I have the limit as n goes to infinity of, I'm left with x in the top, I'm left with n plus 1 in the bottom. Since x no longer has an n with it, I can take the absolute value of x out and just look at the limit as n goes to infinity of 1 over n plus 1. Now that's always positive, so absolute value bars, that doesn't really matter. Now this goes to 0. And no matter what value of x is, that value times 0 is always less than 1. So this is actually going to be convergent for all real numbers. I'm going to say that one more time. The limit goes to 0. So no matter what value I plug in for x, number times 0 always less than 1. So x can be anything, and this is always convergent. Okay, you plug in a couple of them, 4 to the n, -4 to the n, 10 to the n. It doesn't matter. Anything on that interval from -infinity to infinity, anything for all real numbers of x is going to be convergent. All right, let's look at B. Let me erase this real quick. I did find out that I could pause and erase and then unpause, and then here we are with a blank screen. Yay, it's like magic. Okay, so let's use the ratio test here on B. So I'm going to have n plus 1 factorial x to the n plus 1 all over, oh, that's messy, hold on. All over n factorial x to the n less than 1. All right, when I go in and do my canceling here, I'm going to be left with n plus 1 in the top and an x in the top, and then all over 1. And so this is going to end up going to infinity, which is never less than 1. So this is only convergent at the center, okay? Because this goes to infinity, x times infinity is never less than 1. So this interval is only at x equals 0, and my radius is 0. This is only convergent right at the point. It's only convergent if x equals 0, right at the center, okay? All right, last one. So let's look at the limit as n goes to infinity of x minus 2 to the n plus 1 over n plus 1 plus 1, 3 to the n plus 1. Now instead of dividing by n, I'm going to multiply by the reciprocal. Okay, let's simplify this. The n and the n cancel here. I'm left with x minus 2. 3n and 3n, I'm left with 3. And then it looks like I get n plus 1 and then n plus 2. Anytime we do this, we are always going to end up getting x minus the center with no n's left that you're able to pull out. Okay, and then it's always going to be dependent then on what your limit with everything else left over is going to be. All right, using our long-term rules, I know this is going to be 1/3, so absolute value of x minus 2 times 1/3 is less than 1. And then let's solve some inequalities here. So 3. And then this means that the center is at 2, but this absolute value inequality means that this must be sandwiched between -3 and 3, right? Anything inside that absolute value bar, once you subtract 2, it needs to be between 0 and 3. But since it's absolute value bars, that means it also can be like between 0 and -3, if you will. So we undo the absolute value bars like that. And then we can add 2 to figure out what that interval is. So -1 to 5. Now this is centered at 2, right? If you go back to the very beginning, x minus 2 means this is centered at 2. So if you look at a number line, and my center is at 2, this is my radius. Okay, if you go back to our definition, x minus a less than r, your radius is 3. So you need to go 3 this way. You need to go 3 this way. And that is your potential radius of convergence. This is the only example we have where we have an actual like interval that's not everything or just the point. So remember what I said before, we have to test these endpoints. So I have to test -1 and I have to test 5 and see if at those x values I'm convergent or not. So I'm going to go to like a lighter green here. If x is equal to -1, we then have the series -3 to the n over n plus 1 times 3 to the n. That is the alternating series, -1 to the n over n plus 1. And that converges by alternating series test. If I plug in x equals 5, let's see. If x equals 5, I then have positive 3n, n plus 1, 3 to the n. Series is 1 over n plus 1. That is divergent. Okay, it models 1 over n. You can just say divergent for me, that's totally fine. And so my final answer here is I'm going to put an equal sign with -1 or a box parentheses, a squared parentheses with 1, but not at 5. So it's okay if x equals -1, it's still convergent at that point, but not at 5.